Hold on, just 1 second. Okay, so this is really week 5, and now we're trying to cover both week 5 and week 6. And then for week 5, we're going through discrete probabilistic modeling. So in this case, one of the key uh, application of this would be something called transition probability. So we would have some sort of example shortly, and then you would be able to know what I'm talking about very quickly as well. And then we can briefly discuss what's the relationship between some of this discrete probability modeling techniques and the linear regression. Um, so we talked about, previously actually the first 3 weeks in general is not as bad as look, especially first 2 weeks. I hope you actually have that feeling as well. And here we talked about, developing models using proportionality and determining the constants of that proportionality. And here we are going to allow the constants of the proportionality to vary in a random fashion rather than to be fixed. So for example, this would be the example. So this one would be one of the ways to model discrete state probability, but with a transition probability. For example, if you think about this example, rental car example, that is to say that someone borrowed, get a car rental from location 1, and then there's a certain probability that he would return that rental car to location 1 with a probability P, as you can already see here with this P. But meanwhile, he has a probability of returning that vehicle to the second location. In that example that we have from Miami and Tampa, which would be the discrete state that we talked about here, right? And then there is another possibility that is going from location 2 to location 1. There would be certain probability as well, which is 1 minus q from location 2 to location 1, and there's a probability for q staying in the same location, meaning that he would return that car to location 2 after he got that rental as well. So here I want to give you, I want to bring up something so that I can show you what that meant. Hold on, let me get something, paint maybe. So I really want to see that what we just saw, that graphically can be represented as a matrix as well, right? That's why earlier I have this transition probability, or sometimes people call it transition matrix for this type of example. So in that case, you can think about it, 1 to 1 with a probability of p, and then 1 to 2 with a probability of 1 minus p, and then 2 to 2 with a probability of q, and then 2 to 1 with a probability of 1 minus q, right? So with this type of transition, you can see that every row should add up to 1, and then every so for the second row it should add up to 1 as well. So that would be a transition probability, and then for any transition probability, transition matrix type of problem, you should have this property, that is to say the sum of all the probabilities should be equal to 1. And then once we have this, then because we already know that relationship, and then we could write two relationship there from, because quantity at time n plus 1 would equal to 0.4 plus pn plus 0.7 qn. Some of them are coming from different locations, some of them are coming from the same location. So in other words, the p and q in this case would be p is 0.7 and q is really 0.6, right? So, or the other way around, you got the idea. And then once we have this relationship, the question becomes, in the long run, approximately how much percent of the cars will be in Tampa and how much percent will be Orlando. And then based on that curve relationship, you would be able to solve. The conclusion would be 57% and 43%. 57% would be in Tampa and 43% would be in Orlando. So this would be a somewhat useful tool for some of these companies to think about this problem, right? So with this, actually, next thing that I really want to talk about is something which is not in this slide set, but still worthwhile to take a look. So for example, there is something that I actually put into the lecture notes, which is called not in the lecture notes, it's really in the weekly material, that is called the queuing system. So if you think about a checkout counter in Walmart, in Target, you would be asking, how can I model how many checkout counters I need? Or in a gas station, if you kind of know the arrival and the departure, and then you want to know how many pumps that I should set up. And then potentially even in an intersection, in a traffic intersection, you would be asking yourself a question that how many lanes I should put in a particular intersection, how many of them should be turning right, how many of them should be turning left, especially in the heavy traffic intersections, right? This type of problem is called queuing system, and then usually people think that as something called MM1 server, and M stands for exponential arrival, Poisson process, Poisson arrival, meaning that each individual inter-arrival time into the queue is following an exponential distribution. And then the second, so this is called arrival process. And then second M stands for the servicing process. And then this servicing process essentially says that the servicing also takes an exponential amount of time. In other words, it follows an exponential distribution. We should say that, to be precise, we should say that servicing time follows an exponential distribution. That is essentially saying that for different customers, you may take different amount of time, but the distribution of that time is exponential. And then in order to analyze this type of system, suppose that just for one counter, then just one, this means number of servers. And then in this type of system, I actually have a link that you guys can take a look, and it really have a better explanation. I mean, you have a more detailed explanation, but here I really want to give you a high level of basic understanding of this problem, so you would be able to understand what the video and lecture notes are talking about. And then this number of servers, and then if we want to model this system, the question becomes, let's think about number of customers in the system. Suppose we use number of customers in the system to be the state in the system. If we use this to define the state, then we know that state meaning that the transition state, right? So meaning that there could be 0 customers in the system, could be 1, could be 2, could be 3, right? Potentially could be infinity, right? So then we know that from 0 to 1, that there's certain probability. What is that probability? Because we know there's a possible arrival, so that we know certain arrival rate. Usually we use a lambda to describe that. So that essentially says there's one arrival, and the arrival rate is lambda. So 0 to 1 is certain arrival rate, and similarly 1 to 2, lambda as well, 2 to 3, lambda as well. And then from 1 to 0 would be when someone was finishing his service, the customer, the counter, checkout counter checked out some customer, then you would use a mu to stand for the departure process. And then this becomes a model, which is similar to what we just discussed. You would be able to analyze on average how many customers would be in a queue, and then on average how long people need to wait, and then how long it takes on average for a customer to get out of the system. So as you can see, this particular methodology have a lot of potential applications, and then you can leverage this in many places. Again, you also see something that this system can be modeled as a simulation as well, right? So in which case you want to leverage simulation. In this case, if you think, number one, you have a really strong assumption in terms of arrival, a strong assumption of the departure. So you do need to validate whether the process really, the arrival and the servicing process really follow those two type of distribution, right? And then question also becomes, if can we model other distributions? The answer is yes. And then there's some analytical form that would be able to help you to analyze some of this different variation of this problem. And then, of course, if the distribution no longer hold for these two types, then the only thing that you could potentially do would be simulation. So in other words, you have a random process in terms of the arrival and some sort of other process that you want to model in terms of the servicing, and then you have some other more complicated situation that, for example, someone would change his customer, go to a customer one goes to, initially he was in for number one counter, and then after waiting 10 minutes he decided to go to number two because he saw number two counter has less people. Things in that nature you would be able to simulate, but it would have a really hard time to find an analytical solution for those type of systems. Okay, here I just really give you a high-level explanation of that, what that is. And in the lecture notes in the weekly material, you should be able to see something more interesting, more depth of explanation as well. Okay, so if we continue down this line, hold on. And then this is the same example basically, except that now we have 3 states instead of 2 to model the Republican, Democrat, and independent voting tendencies. And then you can see here that not sure if some of this statistics make sense in the sense that whether it's really coming from real data, but at least you can see that long term who will be winning is kind of showing there from as a solution, right? Okay, let's continue. And then now here, that's really a high-level explanation of the transition probability. How can you model this type of problem in reality? And now we actually kind of switch the gears for a little bit. Let's look at some other things such as we call it component and system reliability. And then reliability is defined as 1 minus F is a failure rate, FT be the failure rate, and then capitalized FT is a probability distribution function. So that's really the reliability can be defined 1 minus probability of failure. And then for a series system, then reliability of that series system is the reliability multiplication of the reliability of each component, and then you get the final reliability of the system. And then for parallel system, you can use R1 plus R2 minus R1 times I2. So this relationship really hold for what you have learned from resistance in electricity, some of this physics class, right? So the resistance of the parallel system would be identical to what we saw here for this one, right? The resistance that you have for different resistant, if it's a series system, it would be identical to what we saw earlier as well. And then a combination of series and parallel system can be modeled as the third equation that we saw here. And then the third topic that we are really covering in this section is what is the how can you model a linear regression? And then as you know, it's basically you have a bunch of points, and then you're trying to fit a linear model. So if we use this x and y, xi and yi essentially just 1 point, 1 observation, and now you have multiple points. Question becomes which would be the best fitted linear line for these observations, right? So you could fit a line like this, you could fit a line like that, and then you could fit a line like this. Then the question becomes which line is really the best? How do you evaluate which line fits all the points better, right? That's really linear regression. And then hope you already know we can set up a set of normal equations by doing partial order derivatives. You would be able to find the best fitting line. And then here is a solution of that best fitting line, which would be that if you can find the slope of that line, if you could find slope and also the intercept, essentially you define the line already. And then it's important to understand what that is. even though here we actually don't have some discussion quite yet. I remember that we will have a discussion because in later we would tell you what's the relationship between the linear regression and optimization. But here I really want to point out what we're trying to do here. So suppose this is one of the lines that we show here, number 3. For line 3, whatever that line is, what we're trying to minimize is this distance. Sum of this distance square, something called sum of square error. So we call it sum of, because here, based on line 3, we have y estimate, right? So something we call it y estimate. So what we're trying to minimize is we're trying to minimize yi minus y hat squared. So this is the error term. This is our prediction error. And then we sum everything together for all the observation. We're trying to minimize this equation. We're trying to find a line so that we can minimize this squared error, subject to something we call it constraint set, subject to the real observations. Right. So this is an optimization problem. That's why later on we have some discussion in probably in 2 weeks we would have some discussion about what is a linear regression indeed. What's the connection between this with the optimization. So for now we can just leave it for now, and then later we would go back there again. So this is really a high level of the introduction of the model. So you can see that with this formulation, when we want to minimize this, essentially what we're trying to do is we could, for a quadratic function, you have ways to minimize it, right? The way that you do it is partial order derivative, which is, suppose this is our objective function, let's call O. So what we can do is we use O, because y hat estimate is a function of a and b, right? We already saw that. Because y hat is a linear function, which is this, and then we're trying to solve this a and this b, so that you know this y hat is a function of a and b, so that if we use objective function, take partial order derivative in terms of a, and also partial order in first order partial derivative in terms of b, and then you set them to 0, and then you would be able to solve that problem. And then the solution should be really this one, a and b. And of course, for quadratic function, what you need to do is not only to do that, setting those up, but also you need to take the second order of derivative to make sure that it is second order derivative in terms of a twice, right? So that you would make sure that second order derivative is larger than 0, so that you know you find a minimum for that function. So that's that. But we really want to just stop there for discussion of this topic, and then we will pick it up a little bit later. But the idea that I'm telling you is that best fitting line is a formulation of minimization problem, and then you take partial order derivative, you find that a and b should be equal to these. That's a solution of the partial order derivative equation set. And then if we continue here, there's some important discussion, something called error sum of squares, sum squares of error, which essentially is the formulation that I just said, which is a yi minus that y hat, which is an estimate. That's why if you want to minimize SSE, you use partial order derivative of partial first order derivative of SSE in terms of A, and first order derivative of SSE in terms of B, set them to 0 and try to find A and B. And then discussion of total corrected sum of squares, which is each observation minus the average of all the y's. So in this chart, if all of these are the observation, then you can consider that this would be probably the y bar, y average of all the observations. And what's the distance between each observation and this y bar? Use that distance and then sum them together. That is the SST. And then what is regression sum of squares? It is SST minus SSE. So in other words, how much error that the regression can explain. And then with those three definitions, we can define something called R squared, which is 1 minus SSE divided by SST. Because SSR equal to SST minus SSE, so that you would say that R squared can be further explained as this function. So that it is really that SST, if we use this common denominator, it would be SST minus SSE, so that the numerator is really SSR, right? So if you are familiar or you have some exposure previously on this one, then now you understand why R squared is talking about how good your regression model is. The higher R squared, the better the model is, just because you are able to explain the variance of the data using the model much. If the higher R squared, meaning that you would be able to explain the total error better. Okay, and then one thing that we want to mention that would be we would be able to, after the regression, we would be able to calculate the difference for each error, right? So yi minus y hat, and then let's look at the next slide. That essentially tells us this is called residual. Yi minus y hat would be your residual. And then at the end, you want to look at your regression, you look at the residual plot and see whether it makes sense. One way you look at it, x-axis is really the x values of each observation, and y-axis is the residual. And then some of these type of residual patterns we would like to avoid, just because apparently there are some sort of pattern here, right? So let me get a pen here. Hold on. Yeah, I'm actually trying to get a highlighter from here. Pen. Okay, so you can see here, this type is apparent. It's something called fanning type of residual, which is saying that as x becomes bigger, your error becomes bigger as well. So essentially saying that your model is not doing well when the x value is really becomes bigger. This type of problem we need to avoid. This type of residual distribution we need to avoid. And then the second type is called linear. When x becomes bigger, this is bigger. And then the first one is really that when x is bigger, it could be larger, could be more negative, could be more positive, but it is bigger as well. And then the third one is curvilinear. These three are the types that we should be avoiding. What we really would be looking for would be something called random error so that it has a randomly distributed distribution with a mean of 0, because we do have that assumption, which here in this context we really don't discuss a lot there, but we do have assumption that the error term y is modeled as a plus bx plus error term. And then what we're saying that let's get this error term and draw these graphs, right? And then this error term do have a specific assumption, that is, it is normally distributed with a mean of 0 and a sigma squared being the variance. So in other words, at the end, your residual plot should look like this. Has a mean 0, some of them are positive, some of them are negative, and then average close to 0. And then that's the type of residual plots that we're kind of looking for. So when you do regression, it's always important to go one step further, look at those residual, whether there's a certain pattern, whether you really have issues with that model. Okay, so that is really what we plan to cover for this week. And then beyond that, let's go to next slide set. And this section, we really started talking about optimization, even though because of the limit of time, we probably wouldn't be able to finish everything today, but we would follow through as well, hopefully next time. But here, if you look at what is optimization, and then we can have a definition of optimization, and then talk about linear programming and different ways to solve linear program, and then some numerical search methods which we probably don't even wouldn't be our focus at all. So let's look at section 1 to 5. Earlier in chapter we talked about different methods to find the best model, and then it could be minimize the sum of the absolute deviations and minimize the largest of the absolute deviations, which is the Chebyshev criteria. Is that what it's actually that particular method is somewhat interesting. Unfortunately, we didn't go through live 2 weeks ago, but hopefully you were able to read the book and look at what it meant, and then it can be solved by optimization technique. And then the third one is to minimize the sum of the square deviation, which is the least squares criterion we actually just discussed in the previous 10 minutes ago. And then let's look at what is a linear program. A linear program is, as the name indicates, it's a combination of linear functions. And then you have an objective function that's important to know. You're trying to minimize something, or you're trying to maximize something with certain constraints, subject to certain constraint, and all these constraints are linear in the sense that doesn't have quadratic terms, it doesn't have x times y, it doesn't have x squared, it doesn't have x cubed, things in that nature. So this set of types of family of problem is called linear problem. And then the basic model of any optimization is optimized with an objective function with all the observations, any j in the bigger set of bigger j, and subject to certain constraints. It could be larger than equal to, we call it inequality constraint, and it could be equal to, which we call the equality constraint. And then here there's some certain important things that you should pay attention to. They are decision variables, such as let's use the example that usually we use. That would be you have certain amount of lumber and then you're trying to make number of chairs and number of desks. And then the question becomes, what would be the decision variable? Decision variable could be X number of chairs and Y number of desks. And then you're trying to you're a manufacturer and you want to make a decision on how can I maximize my profit, because we know the price for a chair, we know the price of a table and the desk, and then we're trying to maximize that profit so that you would be able to set up equations such as maximize profit times desk plus profit times chair constraint with the constraint that the amount of chair and the amount of lumber that a chair may need to use plus the amount of lumber that manufacturing a desk need to use should be less than equal to the amount of wood lumber that you actually have on hand. That would be the a classic example. So, and then we would say that the decision variable in this case that we just discussed would be x and y. What I just discussed. X would be number of desks. Y would be number of chairs that we plan to manufacture. And then if profit of desk would be P1 and then would be P2Y. And then what we're trying to do is we're trying to maximize that, right? And then constraint would be, let's call it cost 1 of X plus cost 2 of Y should be less than equal to, suppose I only have 1,000 square foot of the woods. Right, so that would be something that we can use. And then, of course, x has to be larger than or equal to 0, and y could be larger than or equal to 0. And then this would be a linear program that we saw here. And then here, x and y would be decision variable, and then this would be our objective function, and this subject to would be the constraint, and then the right-hand side is really this number. 1,000 in this example. Okay, so that will be an introduction for linear program. And then let's look at from high level, what would be the optimization problems. It could be unconstrained, could be constrained. And then for linear program, it should be there is a unique objective function and decision variable has a power of 1, as we saw just now. It's only powered by 1 here. And then no product of decision variables in the objective function or the constraint. Otherwise, we don't have x times y. If we do have that, it becomes a quadratic function, right? Because it's no longer linear. And then the coefficient of decision variable in the objective function and each constraint are constant. That's important here. So we already know P1 and P2. We already know C1 and C2 as well in this case. So, and then the decision variables are permitted to assume fractional as well as integer values. In this example, we didn't specify that apparently we cannot have 3.5 a fraction of desks in the example, but we don't really have a specific constraint here to say that x has to be an integer, y has to be an integer. In reality, this probably should put in as well, especially for this desks and chair example. And then we would discuss that later as well. It becomes an integer program, and the solution methodology would be quite different as well. Okay. Of course, there are some other types of programs. Here list a couple of them. There would be multi-objective or Go programs, nonlinear program, dynamic program, stochastic program, and also integer program. Integer program would be something that we will discuss in this class as well later in the process. And then we call it MIP in general. Here, this example is called space shuttle cargo. Suppose that this is also called something called knapsack problem. So the idea is, suppose that you want to go hiking and then you only have one bag that you plan to carry with you. The question is, of course, your bag can only contain certain things, right? And then you're thinking about, okay, I need 3 bottles of water, maybe 2 apples, some other things as well. And then the question becomes, how many should I bring with me in the hiking process? And then, of course, 1 bottle of water probably provide you something. Hold on, give me 1 minute. I'll get some water. I'll continue with this knapsack shortly. Okay, thank you. So let's continue here. So knapsack, so that here we're saying that we're trying to maximize something, right? You know that a bottle of water can bring you a certain benefit. Even though here you use C, usually we use C to represent cost, but here is really a benefit. So if you carry certain amount of Y, in this case here says if you take it or if you don't take it. And then if you take Y, and then you will have a return of CJ. And then what I'm trying to do is I'm trying to maximize this total benefit in that knapsack. But we know that that bag can only have certain volume, right? There's a V constraint to say that at maximum, if each Y is taking VJ, and then if you have M different types of items, and then my question becomes which one I should take, which one I shouldn't. That's one constraint, one set of constraint. Second second set would be on the weight. And W would be okay. For the bag, maximum I cannot take because I'm go hiking. I probably only want to take 3, maybe 2 kilograms of stuff instead of 20. So that would be another constraint. So in this case, you would be able to set up this relationship. This problem just as this example. You're trying to maximize something, and then you with certain constraint, right? And then of course, at the end, the decision becomes, oh, I should take 3 bottles of water, 2 apples, and 5 snacks, something in that nature. That would be your problem. And then of course you have a utility function in the sense that what's my benefit of each of the units that I'll be taking. So that's one example. That's an integer problem. And then here, so what we're trying to do here is that sometimes for certain cost functions, we could use some sort of piecewise linear to represent that function. So if our cost function look like this curvature on the left-hand side in A, but on B, you would say that you could use certain piecewise linear to represent this function, right? The first segment would be k1 times x1, and second segment would be k2 x2, etc., etc. And then with certain constraint that x1 is within certain range, meaning that within this range, within different range, so that you would be able to represent this problem. Okay, and then now we actually jump into something else. We probably spend like around another 10 minutes to discuss this as well. So let's see, what we call it as a feasible region. Let's look at this example first. It's called Carpenter's problem that I discussed earlier. Suppose that I want to make a x1 unit of desks and x2 unit of chairs. And then my benefit of one desk is 25, and then my benefit of one chair, maybe the other way around. Hopefully desk is more expensive, would be 30. And then I have a certain constraint on the lumber 690, and then I know that when I make one desk I need 5 hours of labor, but for a chair I need 4 hours of labor, and then so I have a labor constraint, right? Because in order to make x1 unit of desks, I need 5 times x1 unit of labor, so that this would be the labor constraint. And then with some sort of non-activity constraint of x1 and x2, so that this is something we call Carpenter's problem. Okay, and then once we have this, now next question is, how can we represent this graphically? Graphically, you can see that for this equation, we know it's really a line. If we set them to equality, we know that is a line in two-dimensional space, right? So in other words, you would be able to find, let's say which one is which. Yeah, constraint 1 is this one. So in other words, you would be able to graphically represent the first constraint just like this line, because you would be able to find the intercept for x1 and x2, and then you would be able to draw that line, which is a straight line, right? And then for the second constraint, similarly, you would be able to do it there as well. And then of course, your x1 has to be larger than 0, which goes to that way. And then your x2 has to be larger than 0 as well, which goes that way. And then for the first constraint, we said it should be less than or equal to 690. That's why, hence, you can see this arrow, because anything underneath this line would be less than or equal to 690. Anything beyond that would be larger than 690. For the second constraint, you can do that the same way. So in order to satisfy all 4 constraints in this case, including x1 and x2 being 2 separate constraints, then you have to only to be limit yourself into this shaded gray area, and then this area we call it as feasible region. That's the idea for this. And then now question becomes, what is our objective function? Objective function is nothing but a line as well, except that we don't know where that line where that intercept should be, right? So you can think about it as multiple parallel lines, and then if we want to find a maximum solution within this feasible region, you can see the maximum should be really there. In that point, you can achieve your maximum. So let's go to the next page. Here we show all the level curves of objective function, and then you are trying to maximize the solution would be here in this example, and then if you want to minimize, the solution should be there, because in this direction, objective function is decreasing, and in that direction, objective function are increasing. Okay, any questions? Okay, so that's really first way that we should look at linear program. In other words, look at the geometric solutions, looking at the graph and come up with a solution. The second solution is something we call algebraic. Algebraic is saying that find all intersection point of constraints and then try to evaluate the objective function of each extreme point. And also we should look at which intersection point are feasible to obtain the extreme point. Extreme point, what we're talking about is not only in this feasible region, but also any intersection. This would be one intersection, this would be one intersection, this would be one intersection, this would be one intersection as well, and then this would be one intersection. And then you have to figure out which one is feasible and which one, and also evaluate the objective function among all of them and pick the one that's optimal. Optimal meaning maximum or minimum. That's the third step, evaluate. Fourth step is choose the extreme point with the largest or smallest value of the objective function, depending on the objective. And then the computational complexity-wise, it is intersection point enumeration. So, but here there's one important aspect that we actually didn't discuss. I don't think it's really actually is here. This is that it's a theorem, and then but we don't really spend like a fair amount of time to prove it is true. But in reality, it can be complex to delve into those details to understand that the maximum, if either a maximum or minimum does exist, it must occur at one of the extreme points. That's the reason we would be able to leverage this approach, meaning just look at the extreme points. And then the next solution method is really the most efficient one. It is called simplex method. And simplex method is nothing but what we have studied in high school, something called it's called elimination. It's called a variable elimination process. So the way that it should be done is you start with a Tableau format, and then you have an initial extreme point, and then you do some sort of optimality test, and then you test feasibility, and then you do pivot, which is the elimination, which is really the key for the simplex method, which is called pivot. And then you try to do this process multiple times, repeat 3 to 5 until you find your optimal extreme point. Here, unfortunately, actually, I don't have time to explain an example, but once you look at it, you just follow through the example, you would know how you'll be able to solve it. In reality, you probably use some sort of solver. You don't really go through this manually, but it's worthwhile to go through this example at least once, so you get the gist of the, you get a good understanding of the gist of the idea, so you would be able to feel comfortable with the methodology as well. And then beyond this, those 3 ways to think about linear programming solution methodology. And beyond this, you can look at 2 types of analysis. That would be sensitivity analysis, and then it has 2 different angles. First angle is called what is the sensitivity of the optimal solution to the change in the coefficient of the objective function. So suppose that because we have objective function a1x1 plus a2x2 maximize, for example, the question is really asking is, what is the effect of changing the value of the profit for each table, one of the decision variables? In other words, if I have instead of A1 is A1 plus a beta being my objective, being my value, what would be the impact for the whole thing? That is one way to look at the sensitivity. The second way would be, what is the change of the objective function if one extra resource is available? So in this formulation that we saw, instead of 690, if we have 691, how much my objective function would change? So this one is the second way that you can look at it. The economic interpretation of this would be the marginal value, and the economic interpretation of this would be something called shadow price, so that you can look at economic definition of this would be shadow price. So you can look at one extra unit of particular product, how much it should be worth. So this is all connected. I already goes to economics, right? Shadow price is relevant to optimization. So we actually have one point later down the road we would look at that as well, but at least here I want to give you guys this heads up as well. So and then this is really just some numeric search method. I don't really want to spend too much time here, but one of the methodology you probably know, something called dichotomous search algorithm. Start from A and B, and then look at the midpoint and evaluate those two values, and then find where it should go, and then to go to find the midpoint of that, again, dichotomous search algorithm. The second one is something called golden section search. Find certain, you would be able to use certain R1 and R2 definition, and then find that golden section. It's just because it's more efficient. And then that's pretty much that I planned for today. And any questions? If not, I hope that you at least I hope that I gave you a good introduction of these two chapters, and then you can continue to read through the textbook and try to answer some of these homework problems. I personally think that it's a good textbook, so you guys should definitely read as much as you could if time permits. Okay, that's everything, and let me know through email if you have any questions. Thank you.